Okay, welcome to topic C of Module 4, Linear Equations. The first lesson in this topic is lesson 15, Slope of a Non-Vertical Line. Okay, so we're going to continue on our theme of linear equations, and we will be looking at slope. And remember that we have made predictions that these graphs will be lines, but we haven't proven it. So we are, over the next 3 or 4 lessons, we will be working towards a proof of that, and developing the idea of slope is going to be part of that idea. Okay, so let's get started with the opening exercise that you have in your notes. Okay, so for this opening exercise, you have graph A and graph B, and I would ask you to look at those two lines and just make a conjecture, decide which graph is steeper. So question A says, which graph is steeper? And then also, so this one or this one. And then part B says, write directions that explain how to move from one point on the graph to the other for graph A and B. So we've got each of these graphs has 2 points labeled right now. Obviously there are other points on these lines, but 2 points are labeled. So which graph is steeper? And then write directions to explain how to move from one point on the graph to the other for both graphs A and B. Okay, so pause the video, do that, and then come back. Okay, so did you see that graph B is actually the steeper graph? Think in terms of if this was a mountain and you were walking up it, this one definitely appears steeper. Okay, so the idea of slope is the idea of steepness, like what, how steep or not so steep is a line. So we could write here that under which graph is steeper, we would say graph B looks steeper. Okay, and then for the second part, write directions that explain how to move from one point on the graph to the other for both graph A and B. You could write something like this. So for graph A, I would be starting at this point, and I would be going up 2 and then over 1, 2, 3. So I would walk up 2 on the grid lines and then over 3 units to the right. So 2 units up and 3 units to the right. This kind of feels like how we defined vectors back in the other section that we were working on before. So we could say for graph A, move 2 units up and 3 units to the right. And if I do that, I get from one point to the next point on that graph. Okay, let's do the same thing for graph B. And I'm going to erase here, so. Okay, so for graph B, I want to start it at this point right here, right there. And I'm going to go up 4, it looks like, and over 1, 2, 3. So to get from this point to that point, I'm going to go up 4 and over 3 to the right. Okay, so for graph B, move 4 units up and move 3 units right. 3 units right. Okay, and again, so that would look like up 4 and over 3 to the right. Okay, let's look at part C of this exercise. Okay, so part C says write the directions from part B as ratios and then compare the ratios. How does this relate to which graph was steeper in part B? So if we wrote the ratio of the units, get the right tool here, of the units moved up or down to units over, the first one, graph A, would be 2 to 3, a ratio of 2 units up for every 3 units over. For graph B, we would have the ratio 4 units up to 3 units over. And you might notice that the ratio 2/3 is less than the ratio 4/3. Okay, so how might this relate to which graph was steeper in part B? So it appears that the ratio of units up to units over could be a measure of steepness. So the greater ratio is going to be the steeper graph. Okay, so now in your notes you have 4 pairs of graphs, such as this one. This is pair 1, graph A and B, and you're asked the same questions. Which graph is steeper? Write directions of how to move from one point to the other on graphs A and B, and then compare the ratios and talk about which graph was steeper and how that related to the ratio. So go ahead and pause the video and do that for pair 1, pair 2, pair 3, and pair 4. Okay, check your work on pair 1 right now. Graph A is definitely steeper. Graph B is a very gentle slope. And then directions to move from one point to the other, the points that are labeled here. So on graph A, we would move 4 units up and 5 units over. And on graph B, we'd be moving 1 unit up and 12 units over. Okay, now we're going to write the directions from part B as ratios. So for graph A, we would have a ratio of 4 units up to 5 units over, so that'd be for graph A. For graph B, we would have 1 unit up and 12 units over. So these ratios, 4/5 is greater than 1/12. So the ratio of moving up to moving over is greater in the steeper graph. So how does this relate to which graph was steeper? The steeper graph had the greater ratio. And there's the greater ratio there. Okay. Okay, pair 2. In pair 2, graph A appears steeper. Okay, and then if you look at the directions for how to move from one point to the other, for graph A, we're going to be going 7 up, and that's, you can count that right here on the graph. 1, 2, 3, 4, 5, 6, 7 up, and 1 over to get from one point to the next. And then on graph B, we'll be going 3 units up and 6 over. And so if I write those as ratios, I'm going to have 7 up to 1 over, 7 over 1, and that's greater than 3 up and 6 over, 3 to 6. So graph A was steeper, and graph A had the greater ratio. All right, for pair 3, graph B appears steeper, and the directions for moving for graph A would be to move 1 unit up and 5 units over. And for graph B, I would be going 4 units up and 1 unit over. And now when I write them as ratios, I am going to have for graph A, the ratio is 1 to 5. And for graph B, the ratio is 4 to 1. Okay, so 4 to 1, clearly a greater value than 1 to 5. So graph B had the greater ratio, and is steeper. Okay, so let's look at pair 4. So with pair 4, I'm looking at them and thinking I can't really tell which is steeper. They're very similar. And if I want to write directions on how to move from one point to the other, again, I'm going to count grid spaces. So for graph A, I'm going to move 4 units up and 4 to the right. I really should have been saying right and left on these examples. If I didn't, well, I was wrong. So anyway, so for graph B, I'm going to need to go from this point 3 up and 3 to the right. So move 3 units up and 3 to the right. Correct that there. 4 units up and 4 to the right, or 3 units up and 3 to the right. Okay, so let me get these back on. Let's part C, compare the ratios. So for graph A, we've got 4 units up to 4 units over to the right. For graph B, we've got a ratio of 3 to 3. So in this case, we've got 4 over 4, and if we want to compare that to 3 to 3, these values are both 1, so the ratios are equal in this situation. So this might explain why we couldn't tell which was steeper. So we could say here the ratios are equal. So, so anyway, this could explain, this could be why we couldn't tell about steepness. I ran out of room, but it could be why we couldn't tell about steepness. Okay, so now I'm going to do some examples that you can jot down some notes on. in a blank area on your in your packet. So here's example 1. And so looking at these two lines, think about what you notice. One of them is different from all the lines that we looked at in those pairs of examples. And so what do you notice about these? Okay, so what you might notice is that one kind of leans one way and the other leans the other way. So if I'm going from left to right, this one is heading up. And if I'm going from left to right on this graph, this one's kind of heading down. Okay, so we'll talk about this more in a couple examples. But when you have a line that is left to right inclining or going up, we're going to we want to assign numbers to steepness on these graphs. And that's going to be, that value will be the slope. And so if a line is, when you're heading left to right, if it's inclining, we're going to call that a positive slope. So that's going to have a positive number. Okay? And if, as we're going left to right on this graph, if we see that the line is declining or going down, we're going to assign that a negative slope. So the number for slope will end up being negative for lines like that. And so since we're not dealing with vertical lines right now, so we're not dealing with vertical lines, the only other type of line there is a horizontal line. So, and we'll deal with that in a later exercise. But for now, let's just say that lines that go up as we move from right to left have a positive slope. The ones that go down as we walk from right to left, or yeah, from left to right, sorry, this way, as they go down, those are going to be assigned a negative slope. Okay, so now that we know whether the slope's going to be positive or negative, we'll look more closely at what the number of the slope will be. So we're going to use this diagram. We have the XY axis, and we have a line that's going through the origin at 0, 0. Okay, so we're going to call this line L, and we're going to label a point. We're going to label the origin with P. That's going to be 1 point on the line. And then we are going to come over 1 unit on the x-axis, and we're going to label that point Q. So we're going to have point P and Q, and the length of PQ is equal to 1. Okay, so Q is at 1 unit out there from P. And next thing we're going to do is construct a vertical line that's going to intersect the our line L. So we have a vertical line going through Q and coming up like that. Okay, and where that intersects our line L, we're going to call that point R. Whoops, need my tool there. We're going to call that point R. So now we've got P and R that are on our line L, and we've got Q over here on the x-axis, and we're going to give this line a name too. If I need to refer to it, we'll call that L1. Okay, so so what I want to see is the slope from this diagram. And since I have the situation where this distance here is 1, since that's how I drew my diagram, then the value of the y-coordinate, which is, of course, this value right here for this line, is going to be the slope. And so we're going to give that a letter. The letter that is commonly used for slope, that pretty much everyone uses for slope, is m. So m is the y-coordinate of the point of intersection. Okay, and so the reason for that, again, is because we have this value of 1 down here. So what we want to do here is we want to actually translate. So going back to our geometry units here, we want to translate this whole diagram, or actually the line itself, over so we can see where this hits the y-axis. So what we would have, and your notes are going to say use a transparency to do this. So you could use a transparency. So I'm going to draw what that would look like if I translated it. And we're going to translate along QP. So we're going to take Q and make Q the origin. And so this whole thing is going to shift that direction. So it could look something like this. So the line in blue is the translated line. So this distance here is 1. This distance here is the y-coordinate right here. So because we're going from 0 up to that value, that is the distance. So the y-coordinate is the distance, and we're going to call that m. So the slope here is m over 1. It's m. So if we want to look at an example with numbers, what we're saying is that when we set up this triangle here, that if this distance is 1, then we're going to call this number, the y-coordinate, the slope. Okay, so this could have been translated from somewhere, but this slope would be 2. So in this case, it's maybe a little more concrete to see it with numbers. So we could say over here that m, the slope, is equal to 2. And that would be the y-coordinate right there. Okay, so bear with me. We're going to look at another example of this. So if you're not quite getting it, don't worry. Just hang in there with me. Okay, so and that I'm going to go back and look at that again. So in this example, we can see why lines that incline from the, as we're going from left to right, as they incline up, why they have positive slopes. So now let's look what happens with a line that declines as we move from left to right. So we're going from left to right, this line is going down. So this line we said should have a negative slope. So let's look at how our definition of slope works for that. Okay, so we're going to label this graph in a similar way. So there's our point P, and we're going to come over here 1 unit and put point Q. So remember that the distance PQ is equal to 1. This distance here is 1. And then we'll construct that perpendicular line that goes through Q, and we'll look at where that hits our other line. So let's do that now. Okay, so here's that line, and we'll do the same thing we did before, and we'll label the point of intersection here R. So we've got point P at the origin, we've got point R on the line where it's directly below point Q. So we've got R down here directly below point Q. So we're saying that our definition of the slope is that it's the y coordinate of point R. So again, we're going to translate so we can see what that is. So we'll go ahead and translate the line so that Q lines up with the origin. And that way when we do that, when Q lines up with the origin, then we can read point R, because point R is going to translate right over here. We can read it right off the y-axis. Okay, so let's look at what that translation would look like. Okay, so I have translated our line along vector, along this vector QP, really. So everything, this line, the green line, moved over. It's parallel, right? Because that's what lines are translated to, parallel lines. So it's parallel. It intersects the y-axis right at the same place where this point R is over here. So this distance here is the value m. Okay, so our slope, the slope of our line here is m. Okay, so that's going to be our definition. Remember, that is only because this distance here is 1 and this distance here is 1. Okay, so let's look at a numerical example of this. Okay, so for a numerical example, so here's our diagram. Here's a labeled graph. So here's 1, 1, positive 1, negative 1, negative 2. And here's our line coming through. So this is our point P. This is our point Q, which is now translated to the origin. And here is our point R. So notice the y-coordinate of point R is negative 2. It's this distance right here from the origin to that y-coordinate. So this is why, and this explains geometrically why a negative, or as moving from left to right, a declining line is going to end up with a negative value for slope. Okay, now let's look at an example that doesn't go through the origin of the graph. So we're going to use pretty much the same process and just change it slightly. So for this example, so here's my diagram. I've got my point P I can put anywhere. Here's my line L that I'm trying to find the slope of, and the XY axis over here. Okay, so I'm going to put P somewhere on the line. Next, now that P's on the line, I'm going to mark point Q to the right of point P. So I've drawn L1 is a line parallel to the x-axis, and that allows me to make sure that Q is just directly to the right of point P, and it's 1 unit. So PQ is 1 right there. Okay, so next we're going to construct the vertical line, L2, we're going to call it, and it's going to intersect our line at point R. We're going to call that point of intersection point R. So what we need to do in this case now is we want to find this distance, And we can do that by doing a translation. So let's get a color here. So here's the origin over here, right down here. It's my XY axis. Got a lot of other lines going on, so you got to keep it straight. So I want to translate this line along this vector. I want Q to go to the origin. And so this whole, our line L is going to shift over like that. Okay, so let's see what that's going to look like. Okay, so when we do this translation, point R is going to come over here. It's not a very good line here, but this vector that I'm translating along is going to move point R kind of down and to the left, and it's gonna, I want QR to coincide with the y-axis right here. So our point P is going to be over there. So our line will be coming through here, right like that. Okay, and so my slope is going to be this distance from the origin up to R. So it's going to be the y coordinate of my translated R. Okay, so let's look at what does that look like as a numerical example. So here we have again this diagram here. So this distance is 1. So this could have been translated from anywhere in the plane so that the point Q lined up with the origin. The point P would be over to the left of it for this type of line. And my slope is the value of the y coordinate of point R. So my slope in this case, M, is equal to 1.5. Okay, so that would be the value for this slope, but we really like to express slope as a fraction, so, or as an integer. So if it's not, if it's has a decimal part like this one does, we would convert it to a fraction. And so 1.5 would be the same as 1 1/2, and written as an improper fraction, which is how we want to express slope, we would have 3/2. So a more standard way to write the value for this slope would be m equals 3/2. And while we're looking at this diagram, it would be, I would like to ask you, where do you see the ratio 3/2 on this diagram? Okay, so you can pause the video and think about that a little bit. Okay, now what you might notice is from writing those ratios before, if I draw the grid lines on this, you'll notice that you're moving, to move from point P to point R, I need to go up 3 and over 2. So there's that ratio again that we were looking at that indicated the steepness of a graph. All right, let's move on. Okay, so find exercise 1 in your notes, and you're going to be completing exercise 1 to 6 independently. The directions say, use your transparency to find the slope of each line if needed. Okay, so in other words, if you want to use your transparency, you can. You don't need to. If you can mentally move these over and determine what the slope is, then you could do it that way. So exercise 1 and 2 just ask you to find the slope 3 asks you to compare the slopes in exercise 1 and 2. And then 4 and 5 look again at slopes. Okay, so go ahead and pause the video, work on that, and then come back and we'll discuss them. Okay, so for this first exercise, we have our line is going through the origin, so we don't need to worry about that. It's right there. And it slopes up here. So we've got point Q and point R labeled. The distance PQ, we can check it. It's 1 because this graph is 1 per grid line. I can tell by the numbering on it. And so the distance QR is 4. And so if I look at a translation of this, it would look something like this. I'm going to use my line tool here. Let's see if I can get this line going through the right points. Nope. I'll just use that. It's hard to draw straight lines on this thing. Okay, well, basically it's going right through there. So the y coordinate here is going to be the distance QR, which is our slope. So for this one, the slope m is equal to 4 because it's passing through positive 4 on the y-axis. For exercise 2, the slope m is equal to 3. The reason for that is because this distance, the distance PQ is 1, and the distance QR, if I translated this whole line down and put Q at the origin, R would be up here at 3 on the y-axis, so the slope would be 3. Okay, because this translation takes point R down on that vector because Q is being translated right to the origin. So you can see the vectors here. P would end up right over here. This would be P. Whoops, not R. This would be P. I did it again. P. Q and R, so the line would come through here somewhere like that. Okay, so positive 3 slope for that line. All right, so the next, our next question is going to ask us to compare the lines in exercises 1 and 2. So I don't have them up on the screen here, but you can look at them in your notes. And they might be a little bit hard to compare, but if you look closely, you can see that graph 1, the graph in exercise 1 seems steeper. And the second part of that says, compare the slopes of each of the lines. Is there a relationship between steepness and slope? So the slope of the steeper line was 4, and the slope of the not so steep line was 3. So it would appear that the steeper the line, the greater the slope. The steeper the line, the greater the slope. All right, let's look at exercise 4. What is the slope of this non-vertical line? So once again, we see point P, point Q, and point R. The distance PQ is 1. If this QR is translated over so that it coincides with the y-axis, then the y-coordinate of that would be -1. So for exercise 4, the slope m would be -1. Right there, again, it's that distance QR. It's the y-coordinate of that. Okay, so m is -1. So that works well for us because notice this graph is a declining line as I move from left to right. Therefore, we would expect it to have a negative slope, and when we calculate it, we see that it is. Okay, exercise 5. We've got point P, point Q, which is 1 unit to the right of it, and then point R, where the perpendicular line through Q intersects our line. So remember, the distance QR is going to be the value of our slope. So we want to translate that over to the y-axis so that we can read it, and so that we can see the value. We want Q to go to the origin. So if we translate this down so that Q is here, so we'd have Q here, P would be right there, and so it's a translation along that vector. So R is going to translate right down like so. So we end up with this parallel line here that got translated. My R ends up right here. It ends up at -4, at y equals -4. So our slope, m, in this case, is equal to -4. Okay, so it's a fairly steep decline right there. Let's see, what else can we say about this? Okay, that's good. So let's look now at our last exercise, exercise 6. So what would be the slope of this line in exercise 6? So this is a horizontal line. It has no steepness, we could say. So if we, if we wanted to take this line and translate it down so that our point Q was on the x-axis like we were doing, or at the origin, we could see that the y-coordinate would be 0. So it's consistent with the other examples that we've done. And so we are going to say that the slope of a horizontal line is 0. It doesn't go up and it doesn't go down. So it's right in the middle of those positive and negative slopes. Okay, so let's look back at, let's talk about this. So we notice that the steeper the graph, the greater the slope. And we saw that in exercise 3. It's slightly different with negative slopes. So let's look at exercise 4, which had a slope of -1. And exercise 5, which has a slope of -4. So -4 is actually less than, -4 is less than -1, but we would definitely say that this graph in 5 is steeper than the graph in 4. So what are we really talking about? How can we say that the slope of -4 is steeper than that? So one thing that you might have thought of is thinking of maybe absolute value. So the absolute value of the slope here, now the absolute value of 4 is actually greater than the absolute value of -1, right? Because 4 is greater than 1. And so with negative slopes, we just want to look at the actual value of the number. And the -4 slope is going to be a steeper line because it has a greater absolute value than the -1. Okay, we've got one more example, and then we'll be ready to summarize and go to the problem set. Okay, so this is a problem that you graphed back in lesson 11. So here's the problem, and here is the work that you did, or we did. So here's the statement. Pauline mows a lawn at a constant rate. Suppose she mowed a 35 square foot lawn in 2.5 minutes. Okay, so we wrote for all these different values for minutes, 0 minutes, 1, 2, 3, and 4. We wrote a linear equation based on the fact that she's mowing at a constant rate, and we evaluated it. So for 0 minutes mowing, she mowed 0 square feet. For 1 minute, 14. For 2, 28, and so on. So now if we assume that the points we plot on a coordinate plane make a line, and the origin of the graph is point P, then the graph looks like this. So here's our graph. We've got point P down at the origin, right here. And we've plotted our points, and we have a scale here. The scale on the x-axis is every grid line is 1 minute. On the y-axis, it's a little different. We're going by fives, 5, 10, 15, 20, 25, 30, and so on. So we've got point P. If we move over for point Q, 1 unit, then we notice that's 1 minute, so that's going to be 14 on our graph. So the slope of this line is going to be this distance here, or this value rather, on the y-axis, and that would be 14. So the slope of this graph is 14. And if you, her unit rate, Pauline's rate, Pauline's rate of mowing is 14 square feet per minute. So 14 square feet in 1 minute. So it's 14 per minute, and the slope is 14. Okay, so on a graph of a proportional relationship, the unit rate is the slope of the graph. And that's why slope is also called rate of change. Okay, so the slope is a rate, and we can use slope to determine the rate of an application problem like this. So this is a proportional relationship of a real-life application, and slope gives us her rate that she mows at. Okay, so let's look at the lesson summary and we'll be done. Okay, so we saw that slope is a number. Okay, so it's either positive, negative, or 0. It's a number that describes the steepness of a line. So it's represented by the symbol M. And lines that are left to right inclining, so in other words, if I'm moving from left to right, the line going up, that's going to be a positive slope. If I'm moving from left to right and the line is going down, we're going to call that a negative slope. Okay, and I can determine the slope of a line when the horizontal distance between points is fixed at 1. So here's my horizontal distance is 1. I translate point Q to the origin of the graph and identify the y-coordinate of point R. By definition, that number is the slope of the line. So a slope of the line shown here is 2 because this distance is 2. This up to the y coordinate of that is 2. So the slope is 2. So that's the definition of slope. Okay, so for this problem set, you will be instructed to use a transparency if you want. You don't need to. I didn't in this lesson. Okay, see how you do with slope.